Hi chemists. In this day of notes, we will be focusing on something called transmutations. After this video, you will be able to identify and explain two ways in which transmutations can occur, and we'll also be balancing nuclear reactions. Alchemy. Have you ever heard of this? Alchemy is a science that was used in the Middle Ages with the goal of changing ordinary metals into gold. And way back when you probably started your unit on atomic structure, you learned something about Dalton's atomic theory. And Dalton said that basically when you start out with an atom of copper, for example, you can't change it into an atom of gold. Amazingly enough, though, alchemy is so cool because when we talk about in terms of nuclear reactions, it is possible to change atoms of one substance into another. But it doesn't happen during normal chemical reactions. And so that's really what was missing in the Middle Ages. The modern practice of chemistry started in medieval Europe, in the Middle East. Alchemists around the 16th century believed that by doing certain chemical reactions, you could turn cheap metals into gold. And we know now that no chemical reaction can achieve this goal. However, through transmutations, nuclear chemistry, modern chemists can change one element into another. In a transmutation reaction, the conversion of an atom of one element into another atom of another element is very easy. This can occur in two ways. The first is via radioactive decay, which we've been talking about all along. The second way is when the nucleus of an atom is bombarded with a certain type of particle, such as a proton or an alpha particle, even a beta particle. Many transmutations occur in nature, and we'll talk more about that in Day 4 notes. So for example, in C14, carbon 14, it's made from N14 or nitrogen 14 in the upper atmosphere. This is the reaction that takes place. Notice that we start out with nitrogen and we add it to a neutron, and notice we form C14 and a proton. Many other transmutations are done in laboratories. In fact, on the image in your screen here, you'll see that in the upper right-hand corner, that's called a particle accelerator. The first artificial transmutation was done by Rutherford in 1919. Here's an example of a reaction. So notice we've got N14, we have an alpha particle, and we make fluorine. Eventually, this led to the discovery of the proton. So let's learn how to write transmutation reactions. The good news is it's very similar to balancing chemical equations. So transmutation reactions are written using the following guidelines. First, we have to make sure the sum of the mass numbers in the top left is the same on both sides of the equation. And second, we want to make sure the sum of the atomic numbers, the bottom left, is the same on both sides of the equation. Again, this is equivalent to balancing chemical reactions where you have the numbers of each atom equal on either side. Third, you want to be familiar with the following particles and their notations. We've talked about these quite a bit already, but to remind you, alpha particles are really just helium nuclei. Remember, the 2+ charge is omitted. But you can see it as either one of these, as helium, written as He with a 4/2, or you can see that little alpha symbol with a 4/2. Beta, remember that's similar to an electron. Gamma, a neutron, a proton. So notice that as a proton, you could have it as hydrogen 1n1, or 1n1 for P. And then a positron, which is the opposite of an electron. So make sure you commit these to memory. It'll make your life a lot easier when you're trying to write these reactions. Let's talk about how to write transmutation reaction with an example. So when I look at this, I want to fill in those question marks. I want to fill in that missing information. And so right away, I'm focusing on the stuff that I know. So for example, I know that it looks like the numbers on the top left, both on the left and the right side, have to add up to 243. The reason why I'm saying that is because notice on the right-hand side, it says 242 in the upper left, plus the 1 from the neutron. So that tells me we have to have 243 on the right and then 243 on the left. The other thing I notice is that I've got 94 on the left and 96 on the right. So I'm going to add that 96 plus 0, and so that's 96. So it also tells me that on the left, I need to have an atomic number of 96. So that means for us that the bottom number has to be 2 and the top number has to be 4 for the particle on the left. Guess what? That's an alpha particle. And then in terms of the other substance that we're missing, that one isn't too bad, because if you look on the periodic table, atomic number 96 corresponds to the element Cn. The most important thing is that you make sure that the numbers equal each other on either side. Here's another example. Let's try and figure out what those question marks are on the left-hand side. So to do that, I'm going to notice what I have on the right. So it's 246 in the upper left-hand corner of Cf. And then I also know there's a large 4 in front. So that 4 is going to be multiplied by the 1. So technically what that's telling me is that I need 250 for that top number for both sides on the left to add up. So it might help to do, for example, 250 minus 238, and that'll give you the mass number. And then also I notice right away that on the right-hand side I've got 98 for Cf in the lower left, but then it's plus 4 times 0. So really I'm still looking for 98 in the lower left to be the total on the left-hand side. So that tells me that I'm going to do 98 minus 92, and so that must mean that I'm looking at carbon with 6 protons and a total mass or mass number of 12. This one says write the beta decay for carbon-14. So this is actually really similar to a decomposition. I know we're talking chemical reactions here, not nuclear decay, but go with me here. So it's like we've got C14, just like it says, right? It's got 14 for the mass number and then 6 protons. It's going to decay into a beta particle. So the beta particle I'm going to write like that. Remember, that's an electron. You can put a beta symbol in there if you want instead. Kind of looks fancy, but this is good too. And then I'm going to notice right away that I need a total of 6 on the right-hand side for the atomic numbers, right, to add up to. So that means I have to say to myself, what plus -1 is going to give me 6? And so if you said, okay, that means that it has to have atomic number of 7, you'd be right. And then that would correspond to nitrogen. And then the 14 just comes from the fact that I need 14 for the mass number, because that's how much there is on the left-hand side of the equation. This one says write the alpha decay for radon-222. So I'm going to first start with my radioisotope. The 86 came right from the periodic table, and so did the element symbol. And I'm going to show the decay by just putting an arrow, and I'm going to write the alpha particle first. Again, I have to say to myself, what plus 2 is going to give me the 86 for the atomic number? So if you're thinking 84, you'd be right. You want to look up atomic number 84 on the periodic table, corresponds to PO, and then the 218 plus the 4 is what gives you 222 on the right-hand side for the mass numbers. Let's talk about those transuranium elements. Elements on the periodic table with atomic numbers above 92 are called transuranium elements. All of these elements undergo transmutation and do not occur in nature and are synthesized in the laboratory, similar to the particle accelerator that I was talking about earlier. To synthesize these elements, particle accelerators bombard nuclei with fast-moving particles. Here's an example. That's that particle accelerator, but it's a blown-up version. Okay, chemists, I hope this video is helpful in understanding how to balance transmutation reactions. As always, good chemists need practice. Thank you so much for watching.